Hello there. Last time we saw how to remove unwanted parts of an array, and this time we'll take care of the next step. We'll learn how to arrange an ND array using the sort function. Let's get coding. As usual, we'll start by importing the dataset and displaying it on the screen. All right. So, NumPy's sort function, npSort, takes an ND array and returns a version of the variable, where all the values are arranged in increasing order. To get a better sense of how this works, let's call the function now. We start by what we'll refer to as the default sort code. In other words, we will type npSort and plug in the dataset variable as an input, without specifying any other arguments. After running the cell, we see another 2D array, where each row is rearranged in increasing order. If we quickly check the documentation of npSort, we'll see that this happens because the default for axis is -1. Negative values for the axis argument work just like they do in indexing, namely traversing the array backwards. Hence, unless we specify otherwise, the function is called overaxis -1, which is the last axis. Since the variable lending company data numeric is a 2D array, it has only two axes. The first axis has an index 0 or -2 and refers to rows. Thus, the second axis, the one with index 1 or -1, is also the last axis and will be about columns. In other words, we're rearranging the different columns in every row, which gives us an array where all the rows are sorted. Okay, we said the sorted array is just a version of the original one, so it should have the same shape, right? We can call the shape attribute of the sorted array to verify this. The output reads 1043 by 6, which means the sorted variable consists of 1043 rows of 6 values each. Let's compare that to the original. The result is once again 1043 by 6, so both arrays have the same shape. Right. We mentioned that the default axis is set to -1, but let's see what happens when we change it. In a new cell, copy the code from earlier and set the axis argument to 0. This should result in an array that has all its columns sorted in increasing order. We see 6 columns and many rows full of numbers in scientific notation. Since these can be difficult to distinguish and compare right away, we can tell NumPy to refrain from using scientific notation by fixing the display options in place. We do so by going to a new cell and calling np.set_print_options and setting the suppress arguments to true. This will indicate to NumPy to restrict precision in favor of clarity when displaying the outputs. However, we need to be extra careful when using this technique because these settings will apply to our entire work rather than a single cell. After suppressing scientific notation, we can rerun the previous cell and get a more readable output. All the separate columns seem to be arranged in increasing order, with the lowest values from the column placed in the first row and the highest in the last one. This is exactly what we expected, so the function works as intended. To better understand how the sort function worked for the 0 axis, we can set axis equal to none and explore the result. The output is a 1D array that contains all the values in the dataset in increasing order. This is because setting axis to none informs the function to work with the flattened version of the 2D input. Since the flattened array is 1D, then so is its sorted version, and that explains the output we see on screen. Great job! So far, we've only discussed how to arrange values in increasing order, but what about the opposite? Sadly, NumPy's sort function doesn't have a parameter that automatically changes the order from increasing to decreasing. However, we're going to show you a quick technique that gets us the desired outcome. In a new cell, copy the code for default sorting and run it. We will use this to compare how the output changes with the technique we're using. In the next cell, paste the code once again, but this time add a minus sign before the input variable. As you know, NumPy arrays work very much like mathematical vectors and matrices. Hence, the minus literally changes the sign of every individual element of the input variable. turning positive numbers to negative and vice versa. Therefore, it's equivalent to multiplying the dataset by -1. But to get a better sense of how this affects results, let's run the cell. We get a new array where all the values appear flipped. If we compare the first row of this array to the first row of the output of the default sort, it looks like we've taken all the values, reversed their order, and switched their signs. Hence, the 40 we saw in the first column is now -40 and appears in the last column. Then we have 365 from the second column, turned into -365, and placed in the penultimate column, and so on. Right. So we've reversed the order of the values on the screen, but we've also changed them in the process. Hence, the matrix we see on screen isn't the original array sorted in decreasing order. In fact, the array we see on the screen is still in ascending order. Lucky for us, the fix here is extremely simple. If we add another minus sign, this time at the start of the line, we should be good to go. As we previously discussed, this is equivalent to multiplying by -1. However, this time we won't be changing the input array, but rather the output. If we run the cell, we'll see a sorted version of the lending company data numeric, where the values in each row are placed from largest to smallest. In other words, we've successfully sorted each line of the initial matrix in descending order. If we want to be certain what the second minus sign we added does, simply delete the minus before the input array and rerun the cell. We see a version of the default sort output, where all the numbers have their signs flipped. Therefore, this negative sign only affects the output. After confirming our suspicion, we can add the minus sign back to finish with the values sorted in descending order and rerun the cell. To summarize, the minus sign within the parentheses changes all the elements of the dataset and helps sort them in descending order, while the minus sign at the start of the line reverses the change of the element's value and returns them to normal. Strange, but this is how it works. Therefore, only as we gain more practice with the sort function, we'll get used to this syntax. Nice! So far, we've only discussed ways of arranging the entire dataset rather than individual columns or arrays. Of course, those work just as you would expect, so let's try one out. In a new cell, we call the dataset variable because we want to have a benchmark to compare the outputs. Next, in another cell, we paste the default sort code. Afterwards, we'll use indexing to show we're only using the fourth column as an input. The output is a 1D array containing the values of the fourth column of the dataset in increasing order, starting from -2,870 and ending at 19,001. That means we can use indexing to sort individual columns as well. However, if we rerun the previous cell, we'll see that fourth column of the original dataset isn't sorted. In fact, none of them are. As we said earlier, the sort function returns a sorted version of the original array, rather than sorting it in place. To do the latter, we either need to set the variable equal to the output of the sort function by applying the standard assignment statement, or we can use the sort method. The way the latter works is the following. It takes the array variable, sorts it, and then stores the sorted version over the original. We see no output because the method doesn't return any value, but instead overwrites the original array. If we display the dataset on a new line, we'll see that the fourth column is different from the output of the previous cell, while the rest remain identical. So we've only arranged the values of one column without messing with the rest. Of course, if we also want to arrange and overwrite the entire dataset, we need to remove the indexing and set the axis argument to 0. The output array clearly has all its columns sorted in ascending order, so the sort method successfully overwrites the input array. Fantastic! After learning about npsort, we're ready to discuss one of its related functions called argsort. In the next lecture, we'll explain what this function does and why it can be so useful for sorting. Thanks for watching!